And so we're going to look at the integral test. Essentially what that says is, just to remind you, suppose you've got a series like this fella. If you rewrite this guy, you know, the formula that generates a series as a function, then provided you can prove that it's positive, that it's decreasing, then you're allowed to use the test. And then the integral test basically says you find that guy. And there are going to be two distinct things that come out of that integral. It exists as a number. So the jargon we would say here is it converges. And if it converges to 2 or 22, it doesn't matter. The fact is that the integral exists as a number, as a limit that's a number. And if that's true, then so does your series converge. And then the opposite is that the whole thing diverges. And typically diverging in these questions means that this integral is infinitely large. In this case, that means this diverges as well. So it's a very tidy test. You know, if your guy converges, by that I mean if your integral converges, then so do you. And if you diverge, so does your series. So I guess what we really want to do is a couple of practice questions just to get into the swing of things. So this one is similar to, just looking at the question here. Let's have a look at this one. There's that guy. The conditions, which are these two fellas, number 1 and 2. They have to be met before you're allowed to do the integral test. But since they take a fair amount of time, I'm just going to say that it works and we'll move on. In fact, from what I've seen, and I don't think I've missed any, all of them, the conditions are met, so you can use the integral test. It wouldn't really be a very fair question to give you a question where the conditions weren't met and then they asked you did it converge or not. That seems like a contradiction. Right, take this guy. His real valued version, the guy that we kind of work with, is him, right? It's identical in formula. We just use x's to indicate real values, n here indicates integral values. Can you trust me that I can prove that that's decreasing because I can show you its derivative is negative? Well, at least as long as x is bigger than 1. And I think it's pretty obvious that as long as x is bigger than 1, it's positive. So the conditions are met. So the only thing I'm going to be really focusing on is finding this integral. Well, pretty much most of the time it's a power rule, u subs, or integration by parts. Agreed? What technique would I use to integrate this little guy? X over x squared plus 2. That's a little disappointing.
Partial fractions?
Nope.
U sub.
Yeah, U sub. Now, partial fractions would probably, I'm trying to think what that would look like. X squared minus 4 on the bottom, probably, but there are some situations where more than one technique works, but typically I think U subs is easier to do than any of the others. So the only time I would think about, well, let me show you. See, if you stick a 1 in the top, it's not a U sub anymore. It's that guy, because I know he is, because he's a standard integral. I know it's a little bit different, but that guy would be partial fractions. So why would I choose them? Well, for starters, this one, x squared plus 2 doesn't factor, so there's no way I could do a partial fraction on it. Using a u sub of x squared plus 2 wouldn't help me because the top's only got 1, so those two are out. And I recognise it looks a bit like x squared plus 1, so that tells me it's in the family of the understands, because I know the integral of 1 over x squared plus 1 is the integral tan function. And this one here, our u sub wouldn't work because that plus 1 would get in the way, so I wouldn't use it for that reason. This can factor as an x plus 2x minus 2, so that would tell me to use partial fractions. So you're getting a crash course on what integral techniques would you use in certain circumstances. And as I said earlier, it is possible in some questions that more than one technique will work. So we'll take this guy here, excuse me. And we'll do the u sub. So it's going to be the limit as t tends to infinity of the integral from 1 to t of this guy. And the u sub of choice is that. Then you differentiate with respect to x, you get that. Well, different people do different ways, but if you do the crossover, you get that. And that eventually gives me that 1 over 2x du equals dx. So I go to this fella here, and it now becomes the limit as t tends to infinity of an integral. And what do I have? I have a u in the bottom. I have an x 1 over 2x du. Looks like I'm going to have the limit as t tends to infinity of a half 1 over u du, which in turn, these are long questions, gives me that fella, which in turn gives me that fella. Yes. Is that a question? I'm just zooming through this process because it's pretty standard, it just takes time. Is there anything about those lines that will make sense? We're good. Okay, you're now going to do the limit as t tends to infinity of a half the natural log of t squared plus 1, take away half the natural log of 2. Okay, bad news. Brute force. Basically, if you can put infinity in and make sense of it, you can use that strategy. Isn't the log of infinity infinity, and half of infinity is infinity? So basically, that answer diverges, which means this guy diverges. Oops. Which means this guy diverges. So you integrate it from 1 to infinity. If you get a number, the series converges. If you get infinity, the series diverges. And that particular one was a u sub technique. There's a guy. His real valued equivalent pretty messy function is that guy. I'm going to find the integral from 1 to infinity of him. which in turn means I'm going to find this fella. What technique am I going to use to integrate him? There's really two candidates, but only one of them works.
Thinking by parts.
That would be one candidate. And what's the other candidate?
USUB.
Right, and only one of them works.
Also, shouldn't it be the limit from t goes to infinity instead of t approaching 1?
Ah, you got that deliberate mistake, yes. So back to the question. Integration by parts or USUB? One of them works, one of them don't. If you go down the wrong rabbit hole, you'll get stuck.
USUB.
Is the right one. If you do a USUB of, well, let's just call it x to the 9. Then du is 9x to the 8. Du by dx, you get that guy. Then you get this guy. And this fella now becomes the limit as t tends to infinity of x to the 8 e to the negative u 1 over 9x to the 8 du, which in turn they cancel and you're integrating that guy, which gives you this guy, which returns you back to that guy. You then evaluate it at 1 and at t. See, it works. So why won't integration by parts work? Well, powers of x and e's very often do work with integration by parts, but in integration by parts, don't you have to differentiate one piece and integrate the other piece? Well, I have no problems in integrating or differentiating that. I have major problems integrating this. And even if I differentiate it, won't it have the effect of making the thing bigger rather than smaller? So it'll just work against the process. So that ain't going to happen, essentially. Now, if it had been x to the 8 e to the negative x, that would have been integration by parts. It also would have been a very long integration by parts because I think I'd have to do it 7 or 8 times before I was finished. I mean, I would eventually get it, but I don't think it would be a fair question to ask you just because of the workload involved. Right, now this fella here, it's going to be the limit as t tends to infinity. If you plug in t here, you get negative 1/9 e to the power of negative t to the 9. Takeaway means an add, so you're going to add 1/9 e to the negative 1. I'm not too concerned about this guy because he's a number. What I am concerned about is what's going to happen to this guy when t goes infinite. He only has 2 directions to go, right? He either goes infinite or he goes towards the number. And typically when these guys go to numbers, isn't it 0? They go to, typically at least this guy. If you plug infinity in here, what does e to the negative infinity look like? James? E to the negative infinity. Looks like you're going to say something.
Isn't it still e to the negative infinity? Or, sorry, negative infinity?
Well, let's find out. E to the negative infinity is the same as 1 over e to the infinity. E to the infinity is infinite. The answer is 0. I think you were thinking of some other algebra there. So basically that's 0, isn't it? So that's a number. So it converges. Which means So does that. Based on the kind of answers that I'm getting, or the lack of answers I'm getting, I think you need to get some practice on your integration, because pretty much if you can't integrate, you're not going to get any of these right. And so that's a goal. Sometimes it's just it's early in the morning and you're not 100% up and running yet, so I can understand that. But you do need to, you need to be able to integrate, and especially integrate things that go from 1 to infinity, because that's pretty much the only question you're going to get in this. Okay, you cannot see this, but here is an example of, does this particular series converge or not? So we have an extra step. We need to know what the general formula is so that I can find f of x, right? Okay, if I call this guy 1 over on, would you agree that it's a fraction with 1 on the top? The first one gets you 1, the second one gets you 4, the third one gets you 9, and the fourth one gets you 16, and the fifth one gets you 25. It's a pretty good clue about what goes in the bottom, isn't it? And what does go in the bottom?
N squared.
Right, so doesn't that mean we're just going to work on this guy? Actually, we'll probably work on that guy. And yes, he is positive, yes, he decreases, and yes, it converges when you integrate it. That's something you'll have to prove. Last time we talked about a guy called P-series. Is he a P-series? There's this guy here.
Yes.
And we call him a P equals 2 P-series. And he converges, doesn't he?
Yes.
In fact, as long as P is greater than 1, it converges. And if you know that, or you can remember that, can't you just use that instead of the integral test? So it's a shortcut. Only works for P-series, but it's better than nothing. So suppose I gave you that guy. If you try to do the integral test in that, you are going to come unstuck really quickly. The only strategies that we have are things like U sub, integration by parts, partial fractions, right? None of which work for that. So what I got to recognize is that maybe, at least in this case, it will work. But can't I split it into 2 separate series and figure out what each one is doing separately, and then come to my conclusion at the end? Basically, isn't this made up of 2 P series added together? Right, the first one, that's a P series with P equals 2. Doesn't that converge? The 4 doesn't matter. P series can have 10, 4, 1 on the top. And you don't even need n cubed in the bottom. You can have 2n cubed or 5n cubed and it doesn't matter, right? It's still considered a member of the P series family. In this case, isn't P equals 3, and it also converges. So, conclusion, the series
Because they both
converges.
converge, they can.
Yeah, since they both converge, it converges. Suppose I did the same to some other series and it broke down into 1 over n squared plus 2 over n, right? Just for argument's sake. This guy would converge, because P equals 2 and it's 2 is bigger than 1. Oh, that guy doesn't. That diverges. What's the conclusion if you have a series that's made up of 2 P series, but one diverges and the other converges? You can't say it half converges or it half diverges. You have to fall on one side of the fence or the other, right? There's nobody sitting in the middle.
I'd say it diverges all the time.
And that's your answer. I say it like, if one bit's broke, the whole thing's broke. And to me, diverging means you're broke. So we've seen some integration. This is a little side story that says, you know, sometimes, although they're in the integration test section, you know, these questions are in that section, you can certainly make your life a lot quicker by using the P series shortcut, can you? And there's nothing wrong with that if you see it. Oops. Have we any questions about that? We're good. Okay. Just scanning through the homework, see what's going on. I won't go into the details. I want to integrate that guy. What method will I use? And it's not a P series, it's what integration technique shall I use?
Yusuf?
Like it. Who's your USUP going to be?
Natural log of x.
Well done. Hey, it's coming, right? Took a little while to get into, you know, integration technique mode. Yep. Suppose I get that guy. What integration technique will work for that question?
Integration by parts.
What about that guy?
Looks like a right triangle sub.
Wow. Well done. It would work. God, don't do it. Just don't do it. You know those right triangle subs take about half a day just to do one of the buggers? Just don't do it that way. It would work, and it's totally correct, and it's kind of cool that you recognize that, but don't do it. I think I've said that enough times, right? So if you're not going to do that, what's your backup plan?
Partial fractions?
Yes. Does it look more like a partial fraction thing? Now you can do the old cover-up technique, and that'll go a little bit quicker if you do, or you can choose to do it whatever technique that you've had in the past. It's beginning to come now, isn't it? I'm getting a feel that I'm not staring at a blank wall and everybody else is looking at the ceiling, so I don't ask you, right? You're getting more into the swing of things. Okay. I guess it's a little unfair for me to tell you what method, because it's not so much a method at all. That particular one here doesn't really play well with integration, right? It's not going to really integrate in the way that I've written it. So it's a little bit of an unfair question. If I write it like that, isn't it basically just a power rule? So it's actually not a hard question. The way it's written is the hardest part of the process. Right? What integration technique for this guy? This is a challenge.
I'm thinking rewrite as e to the 1 over x squared times x to the negative third. And then after that, I'm thinking integration by parts.
I like the first step. Change your strategy for the final part.
U sub.
Yeah. You see it now? That guy is actually that guy. And when you do a U sub, it ends up being a remarkably tidy little U sub, right? Not that, it's easy to integrate, right? And that's pretty much it. These guys can all be integrated, and quite a lot of these are very similar to your homework questions, so you should notice the process. You're meant to choose, or not choose, you're meant to test that the conditions are met. I think in quite a lot of these situations, you're probably just going to say it's true. Even if you don't do it, will you at least know how you should do the check, which is in that question there, right? Provided x is bigger than, well, actually, you have to be about 3 just to be sure. Wouldn't that be positive? By the time you get to log 3, it's positive. Can you trust me? God, I wouldn't really want to do it myself, but if you differentiate that, you should be able to prove its derivative is negative. It'd be a really messy piece of algebra, so I understand why you won't do it. But theoretically, right, you should check conditions are met. What you are going to have to do is the integration part, right? That you can't avoid. And don't, because I'm looking at it right now, don't just click convergence and when it says it's wrong, click divergence and move on. Because when we do the final, and I tell you right now, I am giving you an integral test question in the final. No two ways about it, you're getting one. If you just click that box and I don't see any working, it ain't happening. You're just getting none. Because that tells me you guessed and you got lucky. And of course, in the final, don't you only get one guess? So even in that situation, you're 50% chance of guessing the wrong one. So you've got to go through at least the integration part. So don't make that homework a 3-minute homework by clicking converge. Nope, okay, it's diverge. Move on to the next question. That is not the strategy that is successful for a good mathematician. So let's look at our next session called the comparison test. I'll give you some background to it before we actually even show you what a comparison test is. There's 2 series. Do you recognize the top one as geometric? Do you recognize the second one as a p-series? You're going to be using these guys a lot in the comparison test. Let's do this one first. Would you agree that R equals a half so it converges? Common ratio is a half. Absolute value is still a half. Isn't that less than 1? Isn't that why it converges? Okay, would you agree this is a p-series? And this has a p-series, a p equals 3 p-series. And isn't this greater than 1? And isn't that why this converges? The comparison test is a good name for this test. You're going to get a series that isn't one of these, but is pretty close to being one of these. So you're going to compare the series that you're given to either typically a geometric series or to a P series. And it's what the comparison test says, with a few algebraic twists, is that if your guy behaves like a geometric series that converges, your guy will converge. And if it behaves like a geometric series that diverges, your guy diverges. That kind of makes sense, that if you've got a series that's very similar to something that you know converges, then your guy will converge. And the comparison part is the bit that is where the fun is, because you're not going to integrate anything. You're just going to prove that it behaves like it. Okay, so this is the formal definition. If sigma Bn converges. So suppose we have, and it'll probably be one of these two, right? Suppose sigma Bn converges and An is always less than or equal to Bn, then your guy also converges. Now the logic is you have to be smaller than a converging series. Well, like the argument for that's pretty straightforward. Can you imagine you've got a series Bn, B1 plus B2 plus B3 to infinity, and that adds up to 14. If your guy's made up of terms that are always a little bit less than that, won't it add up to something that's a little bit less than 14? And we don't care what it adds up to. Convergence just means we know it adds up to something, right? Now there's two versions of it, or two flavors of it. Suppose you know the series diverges. And also your guy is always bigger than or equal to it. Then logic tells us that your series diverges. So if you're bigger than something that diverges, you diverge. If you're smaller than something that converges, you converge. That would be me saying it in English. Does the logic of that make sense? If your terms are always bigger than something that you know diverges, then you're going to diverge as well. Any questions about that? Oh, thumbs up. I like thumbs up. If you could just wait for a second, I'm going to just zoom in here. Now, where's the difficulty going to lie? Well, you can't just say this guy's smaller than that. You got to be able to prove it in some way. And that's going to be the algebra problem. How can I show or prove that something is bigger or less than something else? So I'm going to start with baby ones and then work our way up. Right. I'm going to do a convenience here. Do you know this n equals 1 to infinity that I've been writing forever? I'm now going to stop writing them. Will you assume that they're there? I know it doesn't save a lot of time, but it saves me some time. Right. Suppose I had, make it cubed. Suppose I had this guy. U subs won't help me. Partial fractions won't help me. And you can't integrate it with any normal technique I know of. So the integral test fails because it can't work, right? You just can't figure a way of making it up. But I should be able to compare it against something. So the first stage in this process is find who to compare it against. And the guys you're going to use are almost always going to be a P-series or a geometric series. Right? That's the go-to guys. So I'm going to look at this fella, and I'm going to do what I call surgery. In the big scheme of things, if you were evaluating this, would you agree that once n hits a billion, won't a billion take away 1 and a billion not really matter anymore as far as the value? Won't there be? So that means not that it's equal to, but it's approximately the same as. Would you agree that that's approximately the same as that? And this, pretty close. That's all you need to do, pretty close. So would you agree that this is 1 over n squared? Now, 1 over n squared is a P series. It's a P equals 2 series. And 2 is greater than 1, so that converges. So I know that this series converges. I have not proved it. And unfortunately, a lot of people only do step 1. I know that it's going to converge. It's not the same as I'm about to prove that it converges. They are different. So step 2, prove it. Well, let's see how that's going to work. Doesn't this guy have to be less than a version of this guy? Agree? So I have to be going like this. Now I'm going to put an n on the top, and I'm going to put a 2n cubed on the bottom. Oops. I'm going to put a half n cubed on the bottom. Went in the wrong direction. And I'm going to say that that is true. So let's see what the argument is. If you have a fraction and you make the bottom of it bigger, won't the fraction be larger? So I'm going to take n cubed minus 1, right? And I'm going to make it smaller. Well, the simple way of making this smaller is just take a half of n cubed. A half of n cubed smaller than n cubed minus 1. Would you agree at least once you get to about 3 or 4? And this fella becomes 2n over n cubed. And this fella becomes 2 over n squared. So my guy is less than him. Do you recognize 2 over n squared? He's a P series. He's a P series that's equal to 2, so he converges. That's the proof. I have to prove that my guy is less than a P series that converges. That's not normal algebra. You don't really get a lot of experience in doing that, but that's what you're going to get experience of now. Okay, let's look at that guy. Who's he going to behave like?
Like a P series?
Yeah. Would you agree a 1 over n squared P series? That means to me it's converging. It also gives me an idea of what I need to do. Don't I need to take this guy and make him less than or equal to somebody, right? Okay. Can't really do much about the 4, so I'll keep it. If this is going to be bigger, doesn't the bottom have to be smaller? Right. If this is going to be a bigger fraction than that, since I'm making the tops the same, don't I have to make the bottom smaller? Smaller denominator, bigger fraction. It sounds back to front, but that's how it works. Isn't 4/7 bigger than 4/8? Make this guy smaller for me. and make him smaller in a way that he's nice and simple. So I don't want plus ones or anything.
Just n squared.
Would you agree this is a p-series? This is a p-series with p equals 2. This is convergent. Wasn't too hard. How about this fella? N squared plus 1 over n cubed plus 2. If you want to get an idea of what this guy behaves like, don't you basically just look at the biggest powers of n? I know that this diverges. So the reason I do this little early test is, if I know this diverges, don't I have to make this guy bigger than somebody? Right? If you want to converge, you have to be less than somebody. If you want to diverge, you have to be bigger, right? So if this is going to be big, then won't this fella be small? Okay, let's see how we can do that. How do you make fractions smaller? Well, don't you make the top smaller and or the bottom bigger? Okay, I want to make the top smaller first. N squared plus 1. If you make it smaller, wouldn't n squared do? I want to make n cubed plus 2 bigger. And I want that 2 to go away. You want to make it bigger? How about 2n cubed? That becomes 1 over 2n. Do you recognize a p-series? Do you recognize a p-series with p equals 1, so it diverges? This is not your typical algebra, is it? We're looking at taking a fraction and making it bigger, or taking a fraction and making it smaller, and at the same time, we're trying to make it a simpler fraction, right? So we're basically trying to leave one thing on the top and one thing on the bottom. How about this fella? A little bit different. Would you agree in this case the log n's a pain? That's the thing that's causing the trouble. Do you think this thing's going to diverge or converge?
Diverge.
Yeah. So if it's going to diverge, would you probably agree the thing to compare it against would be a p-series called 1 over n? And by the way, isn't that true? Isn't that going to be bigger than that? Yeah, after you do n equals 3 or 4. So that one came out really quick, didn't it? You take the original and you compare it against a p-series that you know, and it has to have the property that that's true, and that means that this diverges because it's a p-series, p equals 1. Okay, I'm taking one straight out of the book, the homework. Okay, let's look at that guy. Just looking at that guy, can you tell it's going to converge? Because I can. Doesn't the only guys that matter are the big powers in the long run? And isn't that going to behave like a 1 over n squared? Right, n squared on top. Right, so now I've got the quest. Since I know that this thing is going to converge, do I make it bigger than or equal to, or do I make it less than or equal to? Which direction do you have to prove if it's a converger? This has to be bigger than something, or this has to be less than something. Isn't that what you need when it's converging? Okay. You want to make a fraction smaller, right? You want this guy here to be bigger. Yeah. I should better way of phrasing that. It's a problem with the English language. You are smaller than me, I am bigger than you. Do you know in the sentence I could actually use both phrases and still be true? So I'm trying to be consistent with my English here. This wants to be small, right? Therefore, doesn't this have to be big? Okay, so let's make it bigger. How do you make the top bigger? Well, with a single power of n, right? Without changing it too much. Would you agree that 2n squared will eventually beat an n squared plus n plus a 6? Eventually. Doesn't matter if it's at the start, but by the time you get to a million, won't 2 times a million squared beat a million squared plus some stuff? And if you want this to be big, don't you want the top to be big? Now, what do I need to do at the bottom to make the fraction bigger? It's a contradiction, but it's true. Don't you have to make the bottom term smaller to make a fraction bigger? So take this fella and make him smaller. Would you agree just making n to the 4 is smaller than this guy? And if you tidy this up, don't you get a p series, which is 2, and now it converges? You need to know which direction to go. That's why I do that bit first. So I know what my answer is going to be. But that's like step 1. Step 2 is take your guy and compare him against the guy. Either show you're less than somebody or show that you're bigger than someone. So let me try a made up one. Okay. Now, as far as comparisons go, would you agree this is a 1 over n? Right, so I know it's going to diverge. Agreed? That tells me that I need to take the original. And since I know this is going to be a diverger, don't I have to make it bigger than or equal to somebody? It's important that you know whether you should go big or small, right? Because you could do, I could make that smaller, I could make that bigger, right? I've got to know which direction. So this is going to be big, this is going to be small. Okay. If you want this to be small, don't you make this fella smaller? Would you agree that n cubed is smaller than all of that? You know, n cubed plus stuff, n cubed. N cubed smaller than n cubed plus stuff, right? Now, what do you want to do at the bottom? Don't you want to make the bottom bigger? Give me a single power of n that you can place on the bottom that's bigger than this.
2n to the 4th.
Overkill, but there's nothing wrong with overkill. Wouldn't n to the 4 on its own also work? But nothing wrong with 2n to the 4, and it's totally valid, so don't change it. You know, works good. Now, would you see that cancels down to a 1 over 2n? Do you recognize a p equals 1 series diverges? Okay. Let's put non-standard ones in. Typically, trig functions are horrible things to deal with. Don't they basically bounce up and down like a yo-yo? You don't know where the heck it's going. At least this one's squared, so I know it's going to bounce between 0 and 1 all over the place. And so you might think that's going to be difficult to hem in. But that's going to converge. And the proof of it is basically that that's true. And you might say, wait a minute, how can this be bigger than that? Well, think about it. What's the worst sign squared can ever be? Isn't the best or worse is 1? Won't it always be at least smaller than that? So isn't this a truism? It's true. So it's actually, it was a 10-second question once you realize that. Are we good with this comparison test thing? Right. Let's show you a geometric one. They're less common. Try to find one, but I know that they're around, so give me a few seconds, I'll see if I can find one. Good grief. Finally found one. Yeah. Yeah, they're towards the end. That's why I couldn't get one. Okay, so here's... Now, can you see that this guy here doesn't really fit the P-series one? The P-series is typically full of polynomials. 2 to the n's, 4 to the n's, 7 to the n's, you know, that kind of thing. That's going to be a geometric series comparison. Now, the only guys that matter are those guys. And would you agree that that's 2/5? And if your R is 2/5, won't that mean it's convergent? So I now have this fella. And don't I have to make him smaller? If you're going to converge, doesn't he have to be smaller than whatever's going here? Right. Now, same kind of trick. I want this to be a bigger fraction than this one. Right? And I want the top and bottom to be single terms, basically versions of this fella. Right? Now, if you want this to be bigger, you can't write 2 to the n, because technically isn't 2 to the n smaller than 3 plus 2 to the n? But if you have that issue, can't you just call it 2 times 2 to the n? You know the tricky doubling or halving works really well. Now, what about the bottom? Do you want the bottom to be bigger or smaller in here? I want the bottom to be bigger, or do I want it to be smaller? Which is the best direction? Smaller. Right. Well, in this case, couldn't I just write 5 to the n? But if I wanted to, I guess I could call it a half 5 to the n. Wouldn't that work as well? That's definitely smaller. Now, a little bit of tidying up here. Do you recognize a geometric series? R is 2/5, the absolute value of which is less than 1. It converges. Now this one, I'll give you one more easy one, then one real stinker. How about 3 to the n minus 1 over 2 to the n plus 1? You agree it's a geometric series, family, like? Doesn't it behave like that fella there? Which is what, 3/2, so it's a diverger. So here we go. Take the original, and since you know it's going to diverge, show me the fraction that's going to make that happen. Right. If this is going to be big, that means this is going to be small, right? So make it smaller. Will that make it smaller? Is 3 to the n smaller than that guy? Nope. So can't we stick a half in front of it and make it smaller? Remember the half and double technique? Right. Now, if you want this to be smaller, don't you need to make the bottom bigger? Is that going to work? Isn't doubling it going to work? Say again, James?
Oh, sorry, I said just throw a 2 in front of it.
Yeah, either throw a 2 or a half. Won't that pretty much take care of every situation you could possibly want? If you think it has to be bigger, throw a 2. If you think it has to be smaller, throw in a half. You can do little, sometimes you can do the untouched version, right? You can just use the highest power and it works. But doubling and halving. So you stick these together, basically you're going to get a quarter, 3 over 2 to the n. And would you agree that in this case, the R is 3/2 and so on, and it diverges? Is there a kind of flow to this process now? I know it was a wee bit, what in here, heck is he doing, right? But you see it's got a flow, right? First, you have to figure out with the quick way what the answer is, and then the last part is the proofing, right? So here's a sinker. We gotta know whether this converges or diverges so that I can figure out what the heck to do here, right? On the top, when n is really big, which one of those two numbers really matters? Which one is the one that's going to contribute by far the greatest amount? 2 to the n or 7 to the n?
7.
Agreed. Now, when you're doing a fraction on the bottom, which one of these two is going to contribute the most to the answer? Won't it be 5 to the n? Question, Kenton?
That was 5.
Oh, 5. I got you. So this guy behaves basically like what? 7/5 to the n? So would you agree it's a diverger? It's a geometric series where the r value is bigger than 1. So if it's going to be, if this is going to diverge, don't we go that direction? Okay, we might double, we might half. That seems to be the going rate here. Don't I want the top to be small? Could I do a half 7 to the n or just 7 to the n? Wouldn't both of them work? Me, I just like it. If you don't need a half or 2, I just don't use it, right? What would I need to do to the bottom? Wouldn't I need to make the bottom bigger? And obviously bigger using this guy, right? Because he's the important one. How about 2 times 5 to the n? Wouldn't that work? Do you agree 2 times 5 to the n beats a 5 to the n plus a 3 to the n? Now you might think 3 to the n is big, but you know, 5 to the billion and 3 to the power of billion. 5 to the power of billion is like, you know, 1,000% more important, right? It contributes a lot more to the answer. So what we got here, that gives me an r of 7/5, which is bigger than 1. So we got a diverger. Are we cool then on what's called the comparison test? Okay, I got 1 thumbs up. I'll take that. I'm just zooming around for weird stuff that doesn't kind of fit into the typical set. How about this fella? Converges or diverges, you can't really do the typical surgery. You just got to think a little bit harder. The inverse tan is not a pretty function, agreed? What's the value of the inverse tan when the angle, the 5n, goes infinite on you? What's the inverse tan of infinity?
Negative infinity?
No. Inverse tan of infinity. If you draw the inverse tan function, it looks like this. And there's a number up there and there's another number down there. And we're interested in that number. Last chance.
Is it a 1/2 pi?
You nailed it. Yeah. So isn't that basically a version of 1 over n squared, so I know it converges? 5 over n squared, pi over n squared, a half pi over n squared. Aren't they all n squareds? They're all p series. They're all going to converge. So I would simply just take this guy and say, well, I need to prove that you are less than or equal to somebody. Wouldn't you agree that it's always going to be less than pi upon 2? You're done. That's just a number, so this is a P series with P equals 2, it converges. Okay, let's stick in some decimals, make your brain hurt. What on earth does this thing look like? Well, don't you just use the highest powers? So the fact that I'm not 2, 3, or 4 doesn't really matter in math. Now, if you take one away from the other, don't you get 1 over 2.2? Would you agree that converges? So don't let the fact that the powers are decimals stop you from doing the usual technique. Since it converges, don't we have to go this way? Don't need to do anything to the top because it's quite nice, right? I can leave that guy alone. Don't I just need to make the bottom smaller? I guess I could do a half of that, or I could just use that term. Right, so I could do that or a half of that. Now, doesn't that get me? And we're good to go. Isn't 1 over 2.2 convergent? P series, P equals 2.2, which is definitely bigger than 1. We got a converger. Just checking some guys out here. Got a problem here. I have to know whether it converges or diverges so that I can figure out what direction to make that guy go, right? Do I make him bigger than something, or do I try and prove he's less than something, right? That's the problem. What's your gut feeling? What do you think e to the 2 over n cubed does? Do you think it converges? Do you think it diverges?
Diverges.
Because you think e to the 2n is pretty big and therefore it diverges? Is that kind of your thought process?
Oh wait, no, converges.
So you've decided that e to the 2n doesn't get that big, and therefore it's really a version of 1 over n cubed. It's in the family at least.
Yeah, it's
that's
a smaller over a thing that gets bigger.
Yeah. That gets smaller, right? That gets smaller really quite quickly. So I know that this is going to converge, right? It's going to behave roughly in the family of 1 over n cubed. So I go like this. Right. So I have e to the 2 over n. You know, e to the 2 over n, you can actually put a number down and eventually won't that be less than it? You can imagine e to 2 over 20 is probably about 1.1. So just because I want to be safe, wouldn't you agree it's less than or equal to e squared? Because the next term is going to be less than that and so on. And isn't that a P series with P equals 3? Because P series don't care what number it is, and e squared is just a number. And that converges. Are we good so far? Well, just when you thought the thing was over, I'm going to show you a second test that's called the limit comparison test. And the limit comparison test says if sigma Bn converges and the limit as n tends to infinity of An over Bn equals L, where L is a number that's not 0 or infinity, which is just a fancy way of saying L is 2 or 1.7, right? If this is true, then sigma An converges. And if sigma Bn diverges, and this is a number L and this is true, then it diverges. Now that one's a little bit harder to prove, but basically what it's saying is that if An and Bn are in the same family, then whatever An does, Bn will do the same. So if An and Bn both behave like a p-series, then the ratio will get you a number and you'll be able to prove that they both essentially behave the same way. Okay, so not as useful because it involves some messy math, but occasionally it can be helpful. If a particular series is giving you a hard time, you could use this technique. So for instance, suppose I did n cubed over the square root of n squared plus 1. Let's take this guy. The limit comparison test is much longer and harder to do. So if you can do a comparison test, I strongly suggest that you do it, just for time purposes. But let's figure out how we would do it. The first step is you have to, just like always, figure out who he behaves as. Now, would you agree that this is n cubed, and would you agree this behaves like the square root of n squared? So it behaves like an n cubed over the square root of n squared, which is an n cubed over n. Which is an n squared. Whoa, I overkilled that one. Would you agree that that's going to heck diverge? Not just diverge, but heck diverge, right? But that's fine. It's going to behave like that guy, which means it's going to diverge. Agreed? So let's find out. The limit as n tends to infinity of An over Bn is the limit as n tends to infinity of En, which is this fella, all over this fella, right? Which becomes the limit as n tends to infinity. Can I skip a line and say it's that guy? Won't this cancel some of that and leave it in? Okay, where are we off to now? I need to find the limit of this fella. Any suggestions how I might choose to do it? I don't think L'Hopital is going to be my friend here. Can I do the divide top and bottom trick instead? Okay, divide top by n, divide the bottom by the square root of n squared, which is just a version of n. And you now get the limit as n tends to infinity of 1 over that guy, which gets me 1. And so, since this diverges and the limit is a number, can't we say that that guy diverges as well? Would you agree that the limit comparison test is a little bit more clunky? You've got a lot more work to do, and therefore you should probably only think about using it in a situation where you find it very difficult to, get the second guy, right? The guy on the right-hand side. I'm trying to think of a situation that would force me to do that. I don't know. Could I have done this question just the normal way? I think I could have. Right, so if I'm doing n cubed and I'm doing the square of n squared plus 1, right? Don't I need to just prove that it's bigger than or equal to somebody bad? Okay, if this is going to be big, don't you have to make this smaller? So how about a half n cubed? Don't you have to make the bottom bigger? No, how about 2 lots of that guy? And what's that going to get me? It's going to get me this fella over that, which is going to get me 1/4 of n squared. Boom. Diverges. I'm going to do a quick scan through the homework to see if I can find a question that I might have to do a comparison test, a limit comparison test to. Okay, here's one. N factorial over n plus 1 factorial. You probably have a big problem with that, agreed? If you try to compare it against something. Who does he behave like? Who does he behave like? Diverges, doesn't he? Well, diverges, right? 1 over n plus 1 over n, same guy. Right, so you want to find the limit as n tends to infinity of that horrible thing over that. I'm not doing it, it's a mess, but it can work. I just noticed a situation that I haven't covered. What should that guy do? It's really not written in a format that's going to make your life easy. Does that help? Can you see it's now 1 over n squared and it's going to converge? Okay, we went through that far too quick. Let me figure that out, a better way of saying that. We went through that a lot faster than I predicted. Let's say it that way. I'm always worried that if I do that, just went so quick that you just don't know what the heck I was doing. Do you feel you understand how the comparison test works? You've got a feeling for it's bigger than somebody or it's less than somebody, and your job is basically to prove one or the other, depending on the situation. And there's this guy called the limit comparison test that you probably will never use except maybe in one very unique question where it's kind of weird looking. And, you know, it helps. Then I think we should get started right away on our last one. That way we can finish it tomorrow, and I won't feel quite as rushed. Last chance. Any questions? Anything you're not sure about before we move on? Okay, we're going for it. Called the alternating series test. I think I should do a little hit list of some of the tests that we've got. Don't we have a geometric series test? You know, that basically says if that's less than 1, it converges, right? And if that's greater than or equal to 1, it diverges. Right? Don't we have a p-series test? And that says if p is greater than 1 or equal to 1, it diverges. Get that? It says if p is greater than 1, it converges. It's better. And if it's less than or equal to 1, it diverges. I'll just call it the integral test without going into its details. We have a comparison test. Technically, don't we have a limit comparison test? Beginning to build up quite a few. I've missed one. Do you know which one I've missed? One of the first tests that we actually used.
Harmonic series.
Oh. I'm putting that in because I did miss it. Technically, it's not considered the test, but yeah, it's a test, I guess. But I still miss one. And it does have see it?
Divergence?
Yeah, the divergence test. Remember that one? It says if the limit is n tends to infinity of the individual terms as a number, and that number ain't 0, it diverges. Right. So we have a whole list of guys. There's 9 official tests. This is going to, I guess, be number 8. But by the time we've finished, because we've included some that I probably would call a test if it was me, they're going to be more than 9. So you can imagine that towards the end, if nobody tells you what test to use, isn't your first question going to be, which test will I use on this series? Shall I do a divergence test? Shall I do an integral test? Should I do a comparison test? Should I do a limit comparison test? Is it a member of the harmonic family? Is it a geometric series? And so on and so forth. That's going to be quite a skill set to have. So let's show you an alternating series. An alternating series is one that basically does this. It is a series where it alternates between positive and negative terms. So it goes a half, take away a third, plus a quarter, take away a fifth, plus a sixth, take away a seventh, right? Those kind of guys. If you have a series that's an alternating series, then you only need to prove the following 2 things. First thing says, if the limit as n tends to infinity of an equals 0. And the second thing, and an is decreasing. Then the series will converge. And that is the alternating series test. You prove that the individual terms go to 0, and you prove that the sequence is decreasing. So if it decreases to 0 and it's an alternating series, we'll assume that it's an alternating series, that's why we use it on only those series, then we can prove that it converges. What will be true if the limit of this is not 0? Suppose the limit as n tends to infinity is 5, or, I don't know, infinity. What would be the conclusion then?
Then it diverges.
Then it diverges. So, don't you get both sides of the coin? The alternating series test will tell you whether an alternating series is converging or whether it's diverging. It has to fall one side of the fence or the other, right? Every series has to either converge or it has to diverge, right? They all have to fall one side or the other.
So is this kind of like an expansion on the divergence test?
It is a little bit, but unfortunately, it's only going to work with alternating series, right? So it can only work with plus minus, guys. But it is a little bit, yeah, what you said is quite true. It's like an extension of the divergence test where you get a little bit more mileage, because basically, doesn't the divergence test only tell you diverge? It doesn't tell you if you converge. It only works in one direction. Most tests, don't they have a left and the right hand side? If this happens, it converges, but if that happens, it diverges, right? That's what most tests do. Divergence test only says if this happens, it diverges. If it doesn't, we don't know. It might converge, it might diverge, we don't know. And it's the only one of the tests that have that issue. You see, this guy, you can tell both things. So let's show you some. There's a guy. How do I know that it's an alternating series? Because it's got that guy. But there are other flavors of alternating series. That is also an alternating series. I'll show you the difference. It's minor, but it's important. If you plug in 1 here, won't you get a negative number, -1? So you'll get -1/1, and then the next time you'll get +1/2, then you'll get -1/3, then you get +1/4. Do you see that plus minus that alternating series do? In this case, right, this second version, -1 to the n plus 1. If you plug in 1, don't you get -1 squared, which is +1? So you start with this guy, and you end up with this guy, and then you get this guy, and then you get into that guy. If you think about it, isn't there only 2 flavors of every alternating series test? There's the ones that start with positive and then go negative next, and there's the ones that start negative and then go positive next. What is the connection between these two?
If you add them together, they're 0.
Right. If that's 5, that'll be -5, right? If this is 7, this will be -7. If this is -2, the other one will be +2. If you add them together, you get 0. Can you see as you add down the columns, they cancel each other out? So do you understand then that that essentially means that these are both going to behave the same way, right? They're either both going to converge or diverge. Right, so let's go and pick this guy, because that was the one I did. In this case, the only fella that matters is the 1/n, right? You ignore the -1 to the power of n. That just makes the alternating series arms. This is the guy that we test. Now, I don't think I'm going to get too many problems with what is the limit of this guy as n goes infinite. Would you agree this is what I call brute force, right? You just plug in infinity and you get 0, which is good news, because isn't that the first thing that has to be true? But there's a second thing that has to be true. Doesn't it have to also decrease? Great. So if you call f of x 1/x, which is essentially that guy, if you want to prove decreasing, don't you basically just multiply, use a power rule? And would you agree that that is definitely less than or equal to 0, provided x is 1 or more? The limit is 0, it decreases. You've got a converger. Pretty cool. But there's some extra benefits that most series don't have. Have you noticed that we haven't, with the exception of geometric series at least, haven't we not actually found what the series adds up to when it converges? We just found that it converged and say, look, it converges, guys, that's it. in the geometric series, wasn't there a formula that allowed you to find out what it would add up to? And then we stopped looking. Well, you can't tell what directly what most alternating series add up to that converge, but you can do this. There's a guy called the partial sums. S1 is what you get when you take the first term, right? S2 is what you get when you add the first two terms. S3, you can see where I'm going with this, is what you get when you add up the first three terms. Now, for an alternating series, actually, won't S3 be A1 take away 2 plus A3, or depending on the flavor you get, it'll be that guy, right? But apart from that, don't you just combine? How about that? You combine the terms. That's what S1, 2, and 3 looks like. So let's take this guy, the one we just did, this fella here. Sigma n equals 1 to infinity, negative 1 to the n, 1 over n. And we've proved that it converges. And so I would like to find out what it converges to. And so what I'm going to do is I'm going to find S3. So I'm basically going to take the first three terms and add them up. So what's that? Negative 1 plus a half, take away a third. So that's negative 4/3, add a half. Convert them into 6, negative 8, 6, plus 3, 6. The answer I get is negative 5, 6. Now, I'm not saying that this series adds up to negative 5, 6. I'm just saying that if you add up the first three terms, it becomes negative 5, 6. So what can you do with partial sums is, it can tell you what the error is. Now, the error, or maybe a better term would be the tolerance. Plus or minus 8 to the 4. The next term, in this case, the next term would be a quarter. So that tells me that the sum is negative 5, 6, give or take the fourth term. So I can tell you that this series adds up to a number somewhere in the range negative 156 plus or minus a quarter, right? So at least I've given you an error band on it. And I think I should probably make that look pretty. So how about negative 10/12 plus or minus 3/12? So how about negative 7/12? Well, I can't do negative 7/12. How about that's it? So it could be anywhere between negative 13/12 and it's somewhere in that range. Well, that's better than most, isn't it? Most of them you don't know what the heck it's adding up to. Would you agree, at least for an alternating series test, I can give you some clue to what it adds up to? Now, if I did S5, right, I added the first 5 terms together, wouldn't the tolerance be plus or minus A6, the next term that I didn't use? Great. Right, suppose I wanted to know the answer to 100 decimal places. Then don't I just need to find out what value 1 over n needs to be 10 to the minus 100? And actually that would be 10 to the power 100. So I'd have to do a Google of them. So you can get a little extra benefit out of alternating series that converge. You can tell roughly what they add up to. The more terms you use, the more accurate will be your prediction. Let's try this fella. Who shall I do? Okay. The limit as n tends to infinity of n squared over n squared plus 1. L'Hopital, divide top and bottom by n squared. I'll do L'Hopital. So it's going to be 2n over 2n, which equals 1. Don't need to do any more. Conclusion. What do you know about this alternating series test? Diverges or converges?
Diverges.
Now you may say, well, why do I know that? Well, the logic kind of makes sense to me. If this here is basically going to become 1, won't there reach a point in time where you're adding a number that's almost 1, and then you're taking away a number that's almost 1, but then you're adding a number that's almost 1, and then you're going to take away a number that's almost -1. Won't this basically bounce between two values, which we call diverging? So that's the argument for why. I don't need to test that it's decreasing. I don't even care now if it's decreasing, because that won't stop it from diverging, right? It's still going to diverge. Okay, there's an unusual fraction to find the limit. Do you recognize any strategy that you might do to find what it's equal to? There's about 2 ways I could do this.
Like the comparison test?
Well, we're not going to, well, what you said is not mathematically the way to say it. So it may still be true, but the way you said it wasn't the way to say it. Because I'm not doing a comparison test, I'm doing an alternating series test. I'm not allowed to, midstream change my test. But what you said might be true if I think what you're saying is that you want me to do something to this to change how it looks.
Yes, but I'm not sure how to say it.
Okay, can you tell me what to do? Okay, here goes. Can I divide the top and bottom by 5 to the n? Now, won't that fella become 3/5 to the n? And won't this guy here become 1? And won't this guy become 1/5 to the n, right? I'm basically comparing it to 3/5 to the n. Now, what happens when n goes infinite? Won't that be 0? Would you agree any number that's less than 1 to the power of infinity gets you 0, right? A half to the power of 0, for instance. 1 plus 0, which means the limit is 0. Or you could have chosen a little bit more. Is that kind of where your brain was thinking? Maybe I've just found another way that you weren't looking at.
Yes, I apologize. I'm cutting in and out. I think I'm maxing out my data.
Uh-oh, no, I don't know how that works. You could do L'Hopital. If you differentiate this guy, you get 3 to the n times the natural log of 3. And then this guy gets you 5 to the n, the natural log of 3. And then, natural log of 5, sorry. Won't this get you 3 over 5 to the n times some numbers? And then the same argument, won't that get you 0? And therefore it converges. So, alternating series, it certainly has a limit of 0. I'm not going to prove that it's decreasing. Will you trust me it is? It's pretty messy derivatives, but it would work. Right, let's see if we can do this one. Negative 1 to the n square root over square root of n. Now that guy is basically an alternating series that uses that, right? This one's going to be quick, I hope. Would you agree that brute force works really well and its limit is 0? I really did not do anything. If I'm going to call this the real valued version of this function, couldn't I call it x to the negative a half? And so when I differentiate it, I get negative 1/2 x to negative 3 upon 2, which is negative 1/2 over x is 3 upon 2, and that is definitely going to be negative and therefore decreasing, and so it converges. How about this question? That is an alternating series, agreed? But if I'm going to do my alternating series test, don't I have to convert it into sigma notation? So let's see what that looks like. Forget about the plus minuses right now. Would you agree that is a 1 over n? That's easy to do. Okay, now we've got the plus minus. There's really only two choices. Which one of them generates 1, positive 1, for the first term?
N plus 1.
Nailed it. Now, would you agree that this function is very easy to do the alternating series test to? Wouldn't its limit as n tends to infinity be 0? The real valued version of it, we can then differentiate and prove that it's decreasing, so it converges. Do you recognize that as a member of the harmonic series, but where you've alternated the terms? Which might seem strange to you, so let me write them down. There is your classic harmonic, and this is an alternating series made from them. They are very similar, aren't they? This one is infinitely large, and this one has a limit. You just have to trust me right now, its limit's log 2. What's the difference? Well, oops, I got my sequence out. There we go. When you do these guys, do you notice that it's only every second term that ends up being subtracted rather than added? Now, in the big scheme of things, you would think that probably shouldn't destroy in an infinity. And not only did it destroy it, didn't it really murder it badly? Because actually, the only bit that's left is worth log 2. So, see all these negative a halves and negative a quarters and all those kind of weird stuff? They must have added up, or at least destroyed this infinity, right? So they must have been an infinity themselves. And then you start doing some weird stuff. If I only write down the negative terms, right? If you suck out negative a half, can you see that this is basically negative a half of a harmonic series? And doesn't it make a little bit more sense now that it managed to kill it off? Because two halves make a whole, but if you've got one plus half and one negative half, aren't they essentially killing each other as they travel to infinity? and there's a little bit left over, right? There's a little bit more on one side than the other, and the little bit that's left over adds up to log 2.